We want to find the max and min values of f of x comma y subject to the constraint x cubed plus y cubed equals 16. We'll solve this using Lagrange multipliers, which is based upon the fact that the max and min values of f subject to the constraint g of x comma y equals 0 will occur where the gradient of f is equal to some multiple of the gradient of g. So we can say the gradient of f is equal to some constant lambda times the gradient of g. From here we get the following system of equations, where looking at the components of these gradients, we would have the partial of f with respect to x equals lambda times the partial of g with respect to x. The second equation would be the partial of f with respect to y equals lambda times the partial of g with respect to y. This last equation again is our constraint, g of x comma y equals 0. So notice how our constraint is given as x cubed plus y cubed equals 16, which means our function g of x comma y will be equal to x cubed plus y cubed minus 16, which must equal 0. Now let's go ahead and set up our system of equations. So we'll start with the partial of f with respect to x. So we're going to differentiate e raised to the power of xy with respect to x, treating y as a constant. So we'd have e raised to the power of xy times the derivative of xy with respect to x, which would be y, equals, then we have lambda times the partial of g with respect to x, which notice how would just be 3x squared, again because we're treating y as a constant. For our second equation, we have the partial of f with respect to y. So now we differentiate e to the xy with respect to y, treating x as a constant. So we'd have e to the xy times the derivative of xy with respect to y, which would be x, equals lambda times the partial of g with respect to y, which would be 3y squared. Again, our third equation in our system is g of xy equals 0, which would be x cubed plus y cubed minus 16 equals 0. So now we want to solve this system of equations. So let's solve these first two equations for lambda. So notice here, to solve for lambda, we would divide both sides by 3x squared. So we'd have lambda equals, let's write the left side as y e to the xy, and then we have divided by 3x squared. And then for the second equation, we would have lambda equals, let's write the left side as x e to the xy, and then divided by 3y squared. So because both of these equations are solved for lambda, we can perform substitution to obtain an equation that just contains x and y. And then we'll use this equation to solve for either x or y, and then perform substitution into the third equation, our constraint. So performing substitution, we'd have x e to the xy divided by 3y squared equals y e to the xy divided by 3x squared. And now to clear the fractions, we can multiply both sides by the least common denominator, or we can cross multiply because we have a proportion, meaning this product must equal this product. Let's do this on the next slide. So again, cross multiplying here, we'd have 3x cubed e to the xy equals, here we'd have 3y cubed e to the xy. Notice how both sides contain a factor of 3 as well as a factor of e to the xy. So let's go ahead and divide both sides by 3 e to the xy. Simplifying, notice 3 divided by 3 simplifies to 1, and so does e to the xy divided by e to the xy. So this leaves us with the equation x cubed equals y cubed, which we can use in the constraint. Let's also solve this for x by taking the cube root of both sides of the equation. The cube root of x cubed is x, the cube root of y cubed is y. So now we know that x cubed equals y cubed and x equals y. Now remember, our constraint was x squared plus y squared minus 16 equals 0. Now we'll perform substitution for either x cubed or y cubed, which will give us an equation in one variable. So again, using our constraint, x cubed plus y cubed minus 16 equals 0, let's go ahead and replace x cubed with y cubed. So this gives us the equation y cubed plus y cubed let's go ahead and add 16 to both sides. And we have 2y cubed equals 16. Divide both sides by 2. Gives us y cubed equals 8. Again, we'll take the cube root of both sides of the equation. And the cube root of 8 is 2, since 2 cubed equals 8. So we have y equals 2. So we have y equals 2, but also notice x equals y, and therefore x also equals 2. Which means the max or min value will occur at this point. Now remember, we're looking for both the max and the min, and we only found one location, which means either the max or min will not exist under the given constraint. For our next step, let's go ahead and evaluate the function f of x comma y at 2 comma 2. So we'd have f of 2 comma 2, which would give us e raised to the power of 2 times 2, or e to the fourth. Let's also get our decimal approximation for e to the fourth. Notice e to the fourth is approximately 54.5982. Now to determine whether this is going to be a max or min function value given the constraint, let's select another point that would satisfy our constraint here on the right and see if that value is more than or less than 54.5982. For example, notice how if we let x equals 0, then y would have to be equal to the cube root of 16. So let's go ahead and determine the function value of f of 0 comma the cube root of 16, which would be e raised to the power of 0 times the cube root of 16, which would be e to the 0, which equals 1. So because this function value is less than e to the fourth, we'll go ahead and assume e to the fourth is the maximum of f under the constraint g equals 0, and therefore this also tells us the minimum does not exist under the given constraint. So going back to our question, the maximum value is e to the fourth, which is approximately 54.5982, and we'll say the minimum value does not exist under the given constraint. Now before we go, let's take a look at this graphically. So what we'll do is take a look at the level curves of f of x comma y and also the level curve of g of x comma y equals 0, and see if the gradient of f and g are multiples of one another or parallel at the point 2 comma 2. Here we see the graph of the level curves of f of x comma y as well as the level curve of g of x comma y equals 0. There's a couple things to notice here. First, notice how the level curves are tangent to each other at this point here, which is the point 2 comma 2, and therefore both the gradient of g and the gradient of f are orthogonal to both level curves at this point, which means the two vectors are also parallel and therefore multiples of one another, as indicated by the method of Lagrange multipliers. Now I should mention that these two vectors here are actually scalar multiples of the gradients, just so they fit nicely on the graph. I hope you found this helpful.